And as a special treat after doing that is you get a relatively clean board, mostly. All right, so to start out with, I have a beaker of water of height h and a radius r, a cylinder of water. And the question is, what is the pressure exerted on the bottom of this container? Well, what would cause pressure on the bottom?
The weight of the water?
Yeah, pretty much. Officially, it's the normal force caused by the water because of the weight, but yeah. So we'll just jump straight to weight of water. And what is the formula for weight? You can do better.
Force of gravity.
That is weight, but I'm nitpicking here. How could she have improved upon her first answer?
Force due to gravity?
That is weight.
Gravitational force.
That is weight. The first thing that she said was it's mass times gravity. What did you mean?
I just meant 9.8.
What is 9.8?
Gravity on Earth. The gravity on Earth.
Same issue. What are the units of 9.8?
Is it acceleration due to gravity?
Yes, acceleration due to gravity. Now, you could have bypassed all that if you just said mg, but... All right, so the weight is the mass times the acceleration due to gravity. And mass times the acceleration due to gravity would be weight, or the force due to gravity, or gravitational force. All right, so we have this beaker of water here, and I want to find the mass of it. Now, generally when you deal with fluids, and I don't think I mentioned this before, may or may not have, fluids versus liquids. What's the difference between a fluid and a liquid? In science? Fluids are things that flow, and so that includes gases also. So liquids and gases are fluids. So when you start dealing with fluids, generally when you're instead of writing mass down, you do it in terms of density. And as was written on the board before, density is mass divided by the volume. Or if we just multiply both sides by volume, we have mass equals the density times the volume. So oftentimes, that's just used instead of mass. So this becomes rho v, that's the mass, times acceleration due to gravity. So that's the weight of the liquid that's sitting inside this water. And so the pressure, as talked about earlier, is force divided by the area. So it's just rho Vg divided by the area of the bottom, which is just pi r squared. So as long as you accept the fact that this water does create a pressure down on that. Yep. A mistake here. Oh, no, we can keep going. The volume is basically the volume of the cylinder here, which is just whatever the area of the base is times the height. So this is density times our volume, which is pi r squared times h times g over pi r squared. And we nicely have things that cancel out. Now the fact that the bottom was a circle just made it convenient to do pi r squared, but it didn't have to be, because whatever the area of the bottom is, that's going to cancel out here. And what we're left with is rho g h, where rho is the density, G is the acceleration due to gravity. And H is basically the depth. So as H gets bigger, in other words, as the water gets deeper, there's more pressure, which is something that I think that there were a couple of nods before on Friday that the deeper you go, the more you feel it in your ears. Questions up to here? So now, let's take a bigger container, side view. I'm not going to go for that three-dimensional look. And I'm going to break this up into 3 sections, section 1, section 2, and section 3. So imagine I just got water on here. The pressure's greater down here than it is up here. I just got these 3 things stacked on it. If I did a force diagram, so pull that over here. So pressure is equal to rho G H. Now there is pressure exerted on the sides of it. If this is a container, the pressure pushing on the sides. But whatever pressure I have, for example, over here, whatever pushing on the water this way, I've got some pressure pointing in the other direction also. If we converted it into a force, that's bad wording. If we figured out the force because of that pressure, then they would all cancel out. So any of the horizontal forces involved are neutralized. So all we really care about are vertical, which is what I'm going to do right here. So this has weight acting down, weight 1. We'll put the ground down there. Weight 2. This middle section has some weight to it. And then weight 3. So imagine I got a stack of blocks here. This is, I guess, very similar to box on box on box on ground. But these things are not in free fall. So there is a force acting upwards. And let's see how well this one does. So there is a normal force pushing up on this. We'll call this y sub 1, and then pushing down on that one. There is a normal force pushing up on the middle block and pushing down on the bottom block. And there's a normal force pushing up on the bottom block and then down on the bottom of the container, or on the ground, depends on how you want to look at it. That should be y sub 3. If this is an equilibrium, what does y1 equal? Not looking for a number here, just. If this is an equilibrium, what does the normal force equal?
The weight.
Yep, weight 1 specifically. So this is equal to weight 1. What does y2 equal?
Weight 2.
Are you stopping there? I missed who spoke. You said,
Weight 2.
keep going.
Plus y1.
Yeah. So I have 2 forces coming down and 1 going up. So y2 has to equal to the sum of the 2 going down. So that would be equal to w2 plus y1. But we know y1 is equal to w1, so that's just equal to w2 plus w1. And that's as far as I want to go for this one. Because I have 2 forces acting on this middle block here, directly because of the water, of the surroundings. I have the equivalent of W1 plus W2 acting up, and the equivalent of W1 acting down. That's what's pushing down on it, that's what's pushing up on it. Yes, there's a gravitational force pulling down also. But what I wanted to get to was the fact that the force coming down from the water is different than the force pushing up from the water. And the net force, because of this right here, this combination here is called the buoyant force. And ultimately, it's equal to that. I mean, that's the sum. So if I have a container of water, it would just sit there. It's not like I have this, it's not like part of the water is falling and another is rising. It's just basically sitting there, at least not significantly. So if I stick another object in here, so instead of having it set up like this, I take some sort of object that's not water and I stick it in there, I still have these buoyant forces. I have a force pushing up on it, I have a force pushing down, and the force pushing up is bigger than the force pushing down. The force upwards, if we go back to this right here, the force is just the pressure times the area. Well, the pressure up, well, we have that formula right there. This is the pressure. So it would be rho g, let's make the depth to the bottom h2, the depth to the top h1. So the force acting upwards is rho g h2 times the area of whatever this thing is. This is the force from the bottom. The force from the top, that's what's pushing down, is rho g h1 times the area of my object. So the net force is rho g h2 minus h1 times the area of whatever I'm pushing up on. H2 minus H1 is just the height here. So if I imagine this is a cylinder, which some of you picked on Friday, if that's just a cylinder, then the area of my cylinder times this height, H2 minus H1, is just the volume of the cylinder. So the net force upwards is rho g times the volume of the object. So this is the density right here. This rho is the density of the fluid. Water in my example here, water in what you did on Friday. So we have a formula for buoyant force. Let's just F sub D is equal to the density of the fluid times the acceleration due to gravity times the volume of the object that is in that fluid. So we could find the buoyant force acting on each of us because of the air. Air is a fluid. It has a density, definitely acceleration due to gravity. And we have our volumes.
What does that say by the first force, right on the bottom?
That's top.
Top.
F sub top. And for some unknown reason, I put F sub bottom up at the top of the board and F sub top at the bottom of the board. Probably would have been nice if I'd done it differently. But this F sub top is this force acting down here, and then F sub bottom that way. Any other questions before you are released into the wild? Go for it.